My name's Caleb, this is the Quarter 5 Shot, and these are the physics of disc golf. Disc golf is like regular golf, only cooler. In order to land your disc in the basket in the fewest throws possible, a strong understanding of the physics behind the game is crucial. By understanding how the disc behaves, whole new levels of play are unleashed. A disc is essentially a combination of a wing and a gyroscope. This creates a variety of flights, as well as the need for different types of discs to create them. First off, how does the disc generate lift? Lift is created when a moving flow of air is turned by another object. There are two key theories to explain this. Bernoulli's principle states that as the velocity of air increases, the pressure of it decreases. The curve of a wing makes air go faster on the top of the wing, dropping the pressure and creating lift. The Newtonian explanation focuses on what happens to the direction of the air. Since for every action there's an equal and opposite reaction, forcing the air downward at the end of the wing means that the wing itself is pushed upwards. The reality is that both of these theories account for part of the bigger picture. They don't contradict each other, although neither one effectively explains why the air moves faster on top or why the low pressure forms. These occur because when the air first hits the curve, it continues straight backwards. This effectively creates a void above the disc, and the air is pulled back down to the surface, although not right away. Because of this, the wing creates this low pressure zone. If the disc was moving without spin, this would almost be a complete explanation, but there's a twist, literally. For a disc to fly, it needs both speed and spin. No speed, no lift. No spin, no stability. To understand why spin is so crucial, let's have a look at gyroscopic inertia. Inertia is the resistance an object has to a change in its motion. It increases with mass. This ability to resist changes to spin depends on the speed, or angular velocity, of the object, its mass, and how that mass is distributed. For disc golf, this means that more spin and more mass placed around the edges will create more gyroscopic inertia. However, these two entities can work against each other. More mass makes it more difficult to get the disc spinning, and less mass around the edges makes it harder to keep it spinning. Spin has an impact beyond the resistance to change. When something does try to change the motion of the disc, it behaves in a unique manner. Without spin, pressing down on the nose of a disc does just what you'd expect. It goes down where you press downwards. When I've just thrown the disc and it's spinning, pushing down on the nose does something else. Instead of the front dropping, this side does. Why? First, let's consider just a part of the disc, visualized with this ball, and have a look at the vectors that impact it. When the ball reaches the point where this outside force is applied, it has forces acting in two directions, left and down. The angular velocity of the spin is the greater of the two, so it continues circling around, but it is pushed down slightly and continues in this altered direction. The greatest change in the height of the ball occurs at the side of the disc before it begins to come back down again. This motion is called gyroscopic precession. Because of it, the maximum reaction to the applied force occurs about 90 degrees away from it, along the direction of rotation. Now, back to the disc. How can we apply gyroscopic precession to an understanding of the disc's flight? Consider the following example. Were we to trace the flight path from above, this is about what we would see. There are two critical aspects of this curve to examine. The first is here, where the disc briefly turns over to the right. The second occurs at the end of the flight, where the disc fades to the left. Here, the disc has slowed down significantly as a result of drag. With this being the case, lift is reduced and gravity begins to overpower it, pulling the disc toward the ground. The disc begins falling faster, causing more of the air below the front of the disc to collide with the nose and push upwards. Gyroscopic precession means that it's the area 90 degrees along the rotation that lifts up, and as a result, the disc tilts and fades to the left. The reverse is also true. More speed brings more lift, and if this force is more than the spin can handle, precession again takes effect. Instead of pushing up on the nose, as with fade, increased lift pushes down. 90 degrees away is the right side. It moves down, and the disc rolls to the right. In disc golf, this is known as turn. Here's that same shot again, now accompanied by a view of the disc's own movement. Extra lift pushes down on the nose and causes the disc to turn over to the right. Loss of speed makes the air push up on the nose, and the disc fades left.